Quality of service, QoS, is a collection of techniques that network administrators use to manage and prioritize network traffic based on its importance and requirements. QoS ensures that critical data, such as real-time applications, for example, VoIP, video conferencing, receives preferential treatment to meet specific performance needs. By giving priority to certain types of traffic, QoS prevents network congestion and ensures a consistent user experience across the network. Imagine a scenario where a company's employees are engaged in a crucial video conference with clients, while other users are heavily downloading large files. Without QoS, the video conference quality might suffer due to bandwidth contention, leading to jitter, delay, and dropped calls. With QoS in place, the video conference traffic gets priority, ensuring smooth and uninterrupted communication, while non-critical downloads are limited to prevent them from affecting the conference quality. 1. Traffic classification. Traffic classification involves identifying different types of network traffic and placing them into specific classes based on their characteristics. For example, voice traffic is classified as high priority, data as medium priority, and bulk file transfers as low priority. 2. Traffic policing. Traffic policing controls the rate of incoming traffic to adhere to predefined limits. If the incoming traffic exceeds the specified rate, excess packets can be dropped or marked for lower priority. 3. Traffic shaping. Traffic shaping smooths out the traffic flow by buffering and controlling the rate of outgoing traffic. It can prevent bursts of traffic from overwhelming the network and can ensure a more even distribution of bandwidth among different classes of traffic. In networking, differentiated services, DSCP, and class of service, CoS, are two important mechanisms for implementing quality of service, QoS, in data networks. DSCP, or Differentiated Services Code Point, plays a crucial role in IP header fields. By utilizing a 6-bit code, DSCP enables the classification of data packets into distinct service classes, thus facilitating the prioritization of traffic within the network. Routers and switches use the assigned DSCP values to determine the appropriate treatment for each packet, allowing for efficient handling of diverse applications and services. On the other hand, class of service, QoS, operates at the Layer 2 level and is primarily employed in local area networks, LANs. Its primary function is to prioritize packets based on VLAN, virtual LAN, or port assignments within switches. By assigning specific QoS values, network administrators can ensure that critical data receives preferential treatment over less time-sensitive traffic. CoS is often integrated with DSCP, as the mapping of CoS values to DSCP values ensures end-to-end quality of service implementation, optimizing overall network performance and user experience. In this practical example, we are focusing on classifying voice traffic with a specific DSCP value as high priority and treating all other traffic as default. To achieve this, we use an access control list, ACL, in conjunction with the modular QoS CLI, MQC, on a router. 1. Creating the ACL. First, we create an access control list with the number 101. The ACL allows us to specify matching criteria for packets that will be classified based on their DSCP value. The line Access List 101 Permit IP any DSCP EF permits any IP traffic with a DSCP value of EF, expedited forwarding. This means that any voice traffic marked with DSCP EF will match this ACL rule. 2. Defining class maps. Next, we define two class maps to group packets based on their characteristics. The voice_traffic class map matches packets that conform to the criteria specified in ACL 101. It will include all voice packets with DSCP EF that we want to prioritize. The default_traffic class map using match any includes all other packets that do not match the voice_traffic class. These packets will be considered as default traffic. 3. Creating the policy map. The policy map named QoS_policy is where we define the actions to be taken for each class of traffic. Under QoS_policy, we configure two classes, voice_traffic and default_traffic. 4. Setting priority for voice traffic. For the voice_traffic class, we apply the priority command with a value of 256. This assigns a high priority treatment to voice traffic marked as EF in the IP header. The priority value is set in terms of the bandwidth allocation. 5. Handling default traffic. For the default_traffic class, we use the fair queue command. Fair queuing ensures that non-voice traffic is treated fairly and prevents any single type of traffic from monopolizing the network resources. 6. Applying the policy. Finally, we apply the QoS_policy map to the outgoing interface, Gigabit Ethernet 0/0. This means that the defined QoS actions will be implemented on the packets leaving this interface. By using this configuration, the router will classify voice traffic marked with DSCP EF as high priority and provide it with dedicated bandwidth, while all other traffic will be treated fairly with the fair queue mechanism. This helps to optimize the network performance for real-time voice communications and ensures a better overall quality of service for different types of traffic. Traffic policing is a QoS mechanism used to control the rate of incoming or outgoing traffic on a network interface. It allows network administrators to enforce specific bandwidth limits for different types of traffic, preventing network congestion and ensuring fair usage of network resources. In this example, we are applying traffic policing to incoming traffic on the interface Gigabit Ethernet 0/1 of the router. The command police 100,000,000 inches is used to define the traffic policing parameters. 1 million inches specifies the rate limit in bits per second, BPS. In this case, the rate limit is set to 1 megabit per second, meaning incoming traffic on this interface will not be allowed to exceed this rate. 8,000 inches represents the burst size in bytes. The burst size determines the maximum amount of data that can be sent in a short period before the policing takes effect. The conform action is specified as transmit. When incoming traffic is within the specified rate limit, 1 megabit per second, it is considered conforming to the policy, and those packets will be transmitted as usual without any restriction. The exceed action is set to drop. If incoming traffic exceeds the rate limit of 1 megabit per second, it is considered non-conforming or exceeding the policing rate. In this case, the excess packets that go beyond the 1 megabit per second rate will be dropped, preventing them from congesting the network and ensuring that the specified bandwidth is not exceeded. In this example, we are applying traffic shaping to outgoing traffic on the interface Gigabit Ethernet 0/0 of the router. The command shape average 2 million inches is used to define the traffic shaping parameters. Average indicates that we want to shape the outgoing traffic to a specified average rate. 2 million inches specifies the average shaping rate in bits per second, BPS. In this case, the average rate is set to 2 megabits per second, which means the router will smooth the traffic flow on Gigabit Ethernet 0/0 to not exceed this average rate. When traffic is sent out on the Gigabit Ethernet 0/0 interface, the router will buffer and regulate the traffic flow to ensure that, on average, it does not exceed the specified shaping rate of 2 megabits per second. If the traffic rate is below 2 megabits per second, it will be transmitted without delay or buffering. However, if the outgoing traffic rate approaches or exceeds the 2 megabits per second limit, the router will introduce delays to bring the average rate down to the shaping rate. FIFO is the default queuing mechanism, where packets are transmitted in the order they arrive. However, no priority is given to specific traffic types, which can lead to congestion and negatively impact latency-sensitive applications. PQ assigns strict priority to specific traffic classes, ensuring they are dequeued and transmitted first. This can lead to starvation of lower priority traffic if not configured correctly. WFQ shares bandwidth fairly among different traffic classes based on configured weights. It provides more equitable treatment of traffic without starving lower priority traffic. Low priority queuing is a quality of service QoS queuing mechanism that provides strict priority to a specific class of traffic over other classes. In Cisco iOS, you can configure PQ to prioritize critical traffic, such as voice, by allowing it to be dequeued and transmitted ahead of other non-priority traffic. In the first example, we are enabling priority queuing on the Gigabit Ethernet 0/0 interface to prioritize voice traffic. The command priority list 1 protocol IP high list voice_traffic creates a priority list with the number 1. The protocol IP high part indicates that we want to prioritize IP traffic marked as high priority. The list name voice_traffic refers to an access control list, ACL, with the number 101. This ACL is used to match packets that have been marked with the DSCP value EF, which corresponds to expedited forwarding, commonly used for voice traffic. The command access list 101 permit IP any DSCP F creates an ACL with the number 101. It allows any IP traffic with a DSCP value of EF to be matched by the priority list, making it the voice traffic to be prioritized. Weighted fair queuing is another QoS queuing mechanism that aims to provide fairness and bandwidth sharing among different traffic classes. It assigns weights to each class, and each class is allocated a proportionate amount of bandwidth relative to its weight. In the second example, we are enabling weighted fair queuing on the Gigabit Ethernet 0/1 interface and assigning weights to different traffic classes. The command fair queue enables WFQ on the Gigabit Ethernet 0/1 interface. Once enabled, the router will allocate bandwidth to various traffic classes based on their weights. The command fair queue 64.256 0 inches assigns weights to 3 different traffic classes. The numbers represent the weights for each class in packets. In this case, the weights are set as follows. Class 1, weight of 64. Class 2, weight of 256. Class 3, weight of 0. The class with a weight of 0 will not receive any bandwidth and will essentially be treated as a low-priority class. In a company with a converged network providing voice, video, and data services, QoS can be implemented to prioritize VoIP traffic, voice, over file downloads, data. This ensures that VoIP calls have low latency, minimal jitter, and are not affected by large file transfers, guaranteeing a smooth communication experience for users. We hope this video helped you on your journey towards becoming a cybersecurity expert. Remember to subscribe to our channel and turn on notifications so you never miss out on our latest content. And if you found our videos helpful, please give us a thumbs up and share them with your friends and colleagues. Don't forget to check out the links and description for our Anki flashcards and to donate to St. Jude Children's Research Hospital. Your support can make a real difference in the lives of those in need. Thanks again for watching, and we'll see you in the next video.